All right, so with our study guide, they're asking questions about number 7 and 8 with the table. Now, number 7 says the limit to negative infinity. So let's talk about how do you make a table to negative infinity. Well, first of all, think about the fact that 10 to the 0 is what? 1. So if we want the numbers to be over here past that, we would do negative 10 to the 1, negative 10 to the 2, negative 10 to the 3, negative 10 to the 4, and you do as many negative 10s to the whatever power you need. Now that negative is on the outside of the power, it's not on the inside. So this 10 to the 0 kind of becomes what we think of as zeros in the middle because it's the power 0, but there's no negative on that because it doesn't matter if there is or isn't, because we're wanting to see as the power gets higher, what is happening to the negative numbers. And usually what you'll find is that it'll go off to negative infinity or positive infinity. In other words, they'll get really, really large, or they'll get extremely small negative numbers. If it doesn't do that, then it's going to round to something. And you might need to make it go further out if it looks like they're not moving very fast. If the numbers are getting, very small increments, then what you'll probably want to do is do a few more and see if it's going to round off to some horizontal number like we've been doing before. Does that make sense? All right. And then to do number 8, you're doing kind of right the opposite. You're going to start with that 10 to the 0 is 1, and then you're going to look at 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, and so on, and do as many as you need to see, is it going to infinity, negative infinity, or does it look like it'll round off to a number that would be the horizontal asymptote? Because that's what these tables are supposed to show. They're supposed to show what the end behavior of your graph is. So it only has 3 choices. It either goes to infinity for positive infinity, it goes to negative infinity, or it goes to a horizontal asymptote. So that's what you're doing in those 2 questions. Does that clarify the directions for some of you who are having trouble?
On the second one, I got negative ones on one side and positive on the other, but they were going to the same number. Just put in.
I'm confused on why you're doing both sides for number 8. It only wants positive. Oh, you did both sides? Oh, okay. Now, really, you should pay very close attention to what they're asking for. They're only asking for one side. But yes, they should both go to the same side number, because if it's a horizontal asymptote, both sides will go to the same thing. Now, if it's not a horizontal asymptote, they might not. Because one side of the graph could be going up while the other one's going down, or they could both be going up or both down for infinities. But if for this particular type of thing, you were only really asked to do one side or the other. Now, I wouldn't count off you did both sides. It's just extra work you didn't need to do. All right. Any questions now? Does that clear up enough on that? All right. On 9 and 10, the algebraic method, remember that no matter whether you're doing the negative infinity or the positive infinity, the major part of the problem is looking to see what's the highest power. That's right. That only matters when you're doing a square root, because the square root in the bottom, when you put x or x squared or x cubed or whatever you're putting underneath each one, when you're putting that underneath there, for example, we'll just look at getting this one started. This is number 10, and it's to negative infinity. So first of all, the square root of x squared is x, which matches the highest power on the top. So I'm going to put the correct thing under each one based on I want it to be x when it comes out of the radical. Okay? So if I put x under this and x under this, I got to put x squared under these. But that makes me put a negative in front because it's negative infinity. If it had been positive infinity, I wouldn't put that.
So on the test, or as when we write these, can we just basically do the math in our head, but still write some of it down?
No, whatever. The limit, I mean, this is the algebra work for the limit. So, how much of this you do in your head is totally up to you. But then I want you to actually write, once you get it simplified, I'd like to see what you thought each piece went to. So if like it's 3 over x, then I would expect you to write a 0 down for it. If it's something that doesn't go like that, if it goes to infinity, then write an infinity down. If it goes to a number, if the, because it's a constant or whatever, to show the math calculations. All right, are there any questions that I need to clarify more for 7 through 10 now on the limits? We're okay on that? All right, did you have any problems with questions 4 through 6 where you're taking the derivative first and setting it equal to 0 and trying to find your critical numbers for that derivative, and then you took the second derivative and set it equal to 0, and then all the numbers that you got that weren't inflection points, you plugged in the second derivative to decide is it a max or a min? Or you put the inflection points in the first derivative to make sure that you can figure out if it's increasing or decreasing on each side of it.
I was confused. Yeah, I was confused about that. I done 1, and then 5 and 6, I kind of got stalled with. I got the derivatives on all of them, but when it comes to the test, I didn't know what to do. Like, I didn't know what to do.
Okay, well, let me make up a simpler example to kind of point that out to you.
The test makes sense, but it's just, are you okay with writing an example on the back of our?
Yeah, if you want to write this down, you can. I got to make one that works for what you want, but yeah, I can do that. Maybe I need to look at a calculator before I start saying I can make one off the top of my head. I wanted to have quite a few terms, and that's where it becomes a little difficult to make one of these up off the top of your head. It also helps if I'm not in math print, because I don't do math print good. I do, because I'm not used to it. It's just Zoom 6. That does not do what I want it to do. Let me find one real quick. I don't know. Off the top of my head, I can't make one that does what I want it to do. I want it to have an inflection point. I want it to have a max and a min at least, because that way you can see the two different sides of it. So let me pull one out of the book. Let's see what this one looks like. This one might work. Okay, x cubed minus 6x squared plus 12x. Well, it would help if I get out of the power. Okay. Yeah, this does. No, it doesn't. Okay, I found one. Minus x cubed plus 3x squared minus 2. This may have been one we've already done, but it'll just help you to illustrate what I'm talking about, because we might not have done it with this thought. All right, so if I take the derivative of this, that'll be negative 3x squared plus 6x. Everybody agree? So if I set that equal to 0 and solve, I got to take out a negative 3x, and that'll give me x minus 2. So what are my two critical numbers here? All right, but I don't know what they are yet, okay? I just know that I've got something. They might be max, min, or inflection points. Have no idea. So then I do the second derivative. And
Is the first derivative always like certain things that they show?
yeah, it can only show a max, a min, or inflection point. Usually maxes and mins more than inflection points, but it can show you an inflection point.
If an x matches the second
Right.
derivative, that's an inflection.
Right. If I get one of these two numbers again, I'll absolutely know it's an inflection point. So if I take the second derivative, I get negative 6x plus 6. And if I set that equal to 0 and take out a negative 6, I get x minus 1. Is that right? Did I do that math right? Okay. So I did not get one of those two numbers again, which means I only have one inflection point and a max and a min, because this is an inflection point, always.
So the second derivative is inflection
Yes, second derivatives only give inflection points. They can't give anything else. First derivatives can give max, mins, or inflection points, but most of the time we're not sure about that until we do the second derivative to know that. All right, so based on these directions for the questions that you're asking me about from 4 to 6, this is what you would do with those numbers. You would go back and put the 1 that you got down here in the first derivative. This is called the first derivative test, and that doesn't take very much math since it's 1, because I don't even really need to write the 1's in there because 1 times anything stays the same, and this came out positive 3, which tells me that it's increasing at my inflection point. Now, why is that important to know? Well, it gives me a visual. It gives me a great visual that it's doing something like this at that inflection point. Does that make sense? Okay. Now, as we go into some of our other lessons this week, we are actually going to chart out more information than we do this test with it. And then the second thing you do is you take the second derivative and do the second derivative test with both of these numbers you got in the first derivative, so you can figure out what they're doing concavity-wise. So if you plug 0 into this second derivative, you're going to get 6. And that means it's concave up because it's positive. And concave up happens with what? Max or min? Min. And then if I plug in 2, I get negative 6 times 2 is negative 12 plus 6 is negative 6. So it's concave down. So it's a max. So now that I know all of that, if I had these 3 points, for example, which I didn't ask you to do this in the, I don't think, did I ask you in the directions to graph this set? No. But if I had asked you to graph it, you could plug 1 and 0 and 2 in the original problem, plot those 3 points, and you would know that the min came first at 0, and then it was increasing here at your inflection point, and that you had concave down over here, for example. Does that make sense? Increasing or decreasing? Right. And the second derivative test helps you to figure out if you have maxes or mins with those first derivative numbers. Yeah, if you was going to really plot this, you would have to go back and plot all 3 numbers in the original problem to get the plot, which I think is kind of where we're going with 1 through 3. Yeah. So, now, let's talk about 1 through 3. Yeah, because you got to draw charts.
There was 2 x's for the second, for the first derivative. So if there was more than just 2, you plug all of them.
Every number gets plugged in. But that's why it's so important to do both derivatives before you start plugging them in, because you don't want to take one of these numbers that appears down here in the second derivative that came from the first one and plug it in the first derivative or the second derivative necessarily. I mean, you would... Yeah, well, no, what I'm saying is you don't want to take a number like, let's say 0 which came from the second derivative. Just because I got it in the first, I can't plug it in the second derivative if it's also in the second derivative, because I know it's an inflection point. I could only plug inflection points in the first derivative.
Oh.
Yeah, so...
For the table graphs that we talked about earlier, I wanted to do the one that I knew that I didn't do right. And it rounded out to be the same number. What did you say?
Then that's the answer for the horizontal asymptote.
We don't, so...
If it didn't go off to infinity or negative infinity, it's getting quite close to, let's say, 5. If a number's getting close to 5, then that's your horizontal asymptote, y equals 5. Yeah. All right, so let's look at the directions on the first page then and talk about this first question. And I will go through this one together, and then you'll have 2 still to try on your own. Now, I may not do every little piece of work. I'm going to let you do the work, but I'm going to talk you through all the work I want you to do. Okay, so it says find the first derivative, find the critical numbers using the first derivative test, use a sign chart to determine if the function is increasing or decreasing. Then it tells us to do the same thing with the second derivative and make a sign chart for it for concave up or down. Sketch as a graph to show these points. All right. So first derivative, what we're going to get? All right. Everybody set that equal to 0 and solve. Don't call out the answer. What you get for 0. Give everybody a chance to find out how many numbers they get. All right, you got numbers? You got 2 numbers? Okay, positive, negative 1, everybody agree? All right, so I want you to set your intervals up. So what would this first interval be? Yep, and then what would the next one be? Okay, and, all right. So then, after you do that, you're going to choose, now we're going to stop here for a second. You can come back and fill in the table in a minute. But what I want you to realize is that when you find those critical numbers using the first derivative test, by setting this equal to 0, I can't plug either one of these into the second derivative if I've been asked to do charts. Okay? So this is how this problem is different from the next set of questions. When they ask you to do a chart, then their thought process behind first derivative test and second derivative test is more along the lines of the chart is going to show that test. So if, for example, it changes from positive to negative or negative to positive, we know there's going to be a max or min. But if it stays positive, positive, that's an inflection point. If it stays negative, negative, that's an inflection point, because in the first derivative test, it shows it's increasing at that point or decreasing at that point, and it doesn't change sign at an inflection point. Does that make sense? So we're using that concept of our last problem. We plugged it in the first derivative and saw that inflection point at 1 was increasing. Well, if we have an inflection point, it'll show that. Does that make sense so far? And if it changes sign, we know it's a max or min. And we just got to think about what's increasing, decreasing. What does that tell me? All right, you can come back in a minute and fill that table in. Let's go ahead and show the second part, and then do all your table work at one time. So now what's the derivative of that derivative? All right. And if I set 6x equal to 0, I get 1 inflection point. Everybody agree? X equals 0. Now, when you do that, you've got to take the same intervals you just had and insert this one into it, because all of them have to be in your chart. All of your numbers have to be in the second derivative chart to show the max or min information. So, I tell you what, hold on. Let's see if I can copy and paste this thing down here, because that would really help me a lot, not to have to redraw it totally. All right, so if I want to include 0, won't I have to change my second interval here? From -1 to 0, from 0 to 1, and 1 to infinity. I inserted an extra one, right? Everybody see that? And then I'll be telling about concavity down here instead of increasing or decreasing.
find the value, would you change that to?
Second derivative. So the key here is it's this almost identical type thought process with the second derivative chart. The only difference is, let's talk about what it means. So if it changes from concave up to concave down, what does that make? Connect it together in your mind. An inflection point. If it stays concave up and concave down and concave down, that makes a max. And if it stays concave up and concave up, it makes a min. So by seeing the sign changes, when the sign changes, the second derivative shows an inflection point. When the sign changes in the first derivative, it shows as maxes or mins. It's right the opposite. Does that make sense? That in the second derivative chart, when the sign doesn't change, it shows you maxes or mins. Because the second derivative is all about inflection points. So whatever don't change had to be what you got from the first derivative. So now see if you can fill in those charts. And when you get done filling in those charts, we'll talk about how to wrap up this problem. I'm going to pause the video while y'all do those two charts. Alright, so now we're going to do what it says about sketching the graph, showing these points, and it's going to be a rough sketch. In order to get that rough sketch going, we have to take the values of -1, 1, and 0 and go back and plug those in our original problem. So we're going to find the value of each of these in the original equation, x cubed minus 3x plus 1. Now 0 is easy, because when you plug 0 in any function, the constant on the end is the answer. So we got 1. I can do that one in my head. The other two I probably could too, but I'll let y'all calculate them because I want to make sure we get it right with the positive and negatives and all. But we need these three values because we want to see what your charts have told you. And we're going to go back and talk about the charts a little bit more in depth here in just a second. But I need these three values so we can, as we talk about it, sketch things. All right, what did y'all get for -1? 3. So is 1, 1?
It's
-1. So 1's -1, 0's 1, and -1 is 3. Everybody agree? Okay. Now, let's go back and talk about your chart here. At -1, did it change from increasing to decreasing, decreasing to increasing, or did it stay the same? So when it goes from increasing to decreasing, is that a max or a min? And when it goes from decreasing to increasing, that makes it then a min. Everybody agree? All right. So in the second chart, when it went from -1 to -1, was it down, down? So that still makes it a max, right? All right. And when it goes from on each side of 0, then did it stay the same?
That went to each side 0 down.
Down, up. Okay. And so the next two are up? All right. So that makes this the inflection point, which makes sense because concave down would change to concave up on an inflection point, or vice versa. An inflection point can go from up to down. And then both up makes it a min, makes sense. So now we're going to take that information about increasing and decreasing and up and down and try to graph it. So according to our chart at -1, it goes up and till it gets to -1, and it's concave down till it gets to -1. Does everybody see what I did? Is I took the same two intervals and looked to see what it said. So I'm going to plot the point at -1, 3. And I'm going to make something that's concave down, but going uphill for increasing. Does that make sense so far? All right. Then our chart for the next one, from -1 to +1, is decreasing. But I've got to plot an inflection point, so I need to make it do what it's supposed to do on each side of 0. So 0 was 1. And according to our chart, from -1 to 0, it's down. And then I need to plot the point 1, 1, -1, so that I can show what it's doing from 0 to 1 is up. But it's decreasing that whole entire time on both sides of that inflection point, like our chart said, from -1 to +1, it's decreasing. Then our last interval is from 1 to infinity. According to the first table, 1 to infinity was doing what? Increasing? And now our second chart's saying it's up. Now the only thing we don't have correct on this graph is just the approximate location of everything. We have 3 good points, but we don't have enough points to show where these ends are crossing the x-axis or any of that. But it's a rough estimate, and a pretty good one at that.
So that's what we have to do 2 and 3.
Mm-hmm. And this is really the first 6 steps of, this is like the first 6 steps of the 10-step problems that I want to show y'all that's going to be for your test. And let me ask, actually more than that. Because step 1's always do the first derivative, and step 2's always say if they're vertical asymptotes or cusps, which is a little extra. And then step 3's make a chart. Step 4's make the second derivative. Step 5's make solve, and step 6 make a chart. Step 7 I can't remember.
Would it be set up, put it in the original run?
No, that's 9. 10's the graph, 9's put them in the original problem. Somewhere in there is some limits work, so I might be off one somewhere in there. So actually, between the limits at the back of this worksheet and what we looked at, and what we've looked at the beginning, we've seen all the pieces of the 10-step problems, just not all together. But this is at least, I would say, almost 3/4 of them, what we just did on this problem here. Now, so you've got to finish up the rest of this for homework and be ready for our quiz that we're taking tomorrow, which will take probably the whole period. It'll be just like that, except a little bit shorter. Now, on those other 2 problems with number 2 and 3, when you do your derivative charts and you do your second derivative charts, you have to include vertical asymptotes and cusps, because they're critical numbers that you find out about, even sometimes before you even start the question. So if the problem's a fractional problem, you're more than likely already going to know where the vertical asymptotes are. You're going to do the derivative to see if there are any maxes or mins in it, but your chart always includes all critical numbers. If your original problem doesn't have a denominator, but your derivative, when you do the first one, does, then you're going to include the cusp in the table. And that's very important, because those are critical numbers just as much as max, mins, or inflection points are critical numbers. So all critical numbers get included in charts. But first derivative charts can also put in cusps and vertical asymptotes. They don't have to just be what it is when it's equal to 0. So that's what you got to do on the other 2. I'm sure there's some cusps and vertical asymptotes in there.
There is. Okay.
Yeah, so just be aware of they go into charts as well. All right. And now, Ethan, you can be able to finish your study guide.